developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
Hello, I'm Calvin Stewart, Director of Materials at Extremes. Today I want to tell you about our project, 3D Printing and Sintering in the Vacuum of Space. Our project focuses on a new technology called Bound Metal Deposition. In this technology, a polymer filament is loaded heavily with laser powder bed fusion metal powder. It's printed on a low-cost FDM printer such as the one behind me or the one that already exists on the International Space Station. And then it needs to be debound and sintered to create a 100% metal part. Our goal is to mature this technology and actually transition it from the laboratory in our labs into orbit, to develop it and mature it from a TRL level 2 to 3 or 4. Now there's a lot of advantages for this technology. It's functional for many different types of alloys. We've been able to print pure tungsten leading edges with integral cooling passages and titanium rib structures. We've printed impellers for jet engines, for UAS systems. We've even printed some tiny demonstrators of turbine blades and rocket nozzles. So there's significant terrestrial and in-space applications for this technology, but also much of the maturation for it has already been done on the ISS. Now there are some limitations to this technology that we're planning to overcome. One of them is densification of the parts. Another one is issues of cracks and defects, and also the overall mechanical strength of these components compared to raw materials. But we believe by using vacuum-assisted sintering, debinding and sintering, that we'll be able to produce very clean parts that are dense, and we'll be able to account for shrinkage by oversizing certain sections and be able to deliver something that's viable for space.
I've been focusing on the difficulty of taking this bound metal filament and then making it printable for rapidly prototyping these parts and then preparing them for debinding and sintering. Some of that has involved getting printers that will be able to do this at a high rate of speed. That's through dynamic flow calibration, both through manual and automatic processes, as well as different kinematic systems within the printers that let them compensate for very high rates of speeds. With this, we have been able to print many demonstrators and compare the print quality throughout them, printing things with different heights to see how changes in layer time affects the overall print quality, then printing different test articles to check geometry and how the printer handles overhangs, as well as working toward what are some additional challenges that come with filaments like this that might not come from standard filaments. These are quite fragile, and so they can't be bent as easily or put through the same systems as standard polymer filaments. This comes with issues in extrusion and in feeding, which we have had to overcome and develop methods for moving into the future. We're preparing to do debinding processes with these through TGA to find an effective method, starting from these green as printed parts and working through to fully metal parts.
As previously discussed, bound metal deposition has the potential of offering a rapid and low-cost additive manufacturing process, which could enable the delivery of prototypes and components at a speed of relevancy for air-breathing and rocket propulsion systems. Behind me is an ATOS ScanBox 5120 system that uses structured blue light to optically capture metrology within the scan volume. With the volumetric data, we can then analyze the geometric deviation and distortion of the component throughout the additive manufacturing cycle, precisely comparing the original CAD design to the printed green component, and then finally to our debound and sintered metal component. Through this process, we expect to gain key insight into the powder rheology, sintering, and then how to compensate through iteration the initial design to produce the desired component geometry.
So to close out phase 1 of this project, these first 6 months, we've completed a substantial amount of work, from procuring various metal-bound filaments, including copper, multiple forms of stainless steel, titanium, and other alloys, to developing baseline 3D printing parameters. How do we actually 3D print these metal-loaded filaments? How do we also ensure good dimensionality in those components? We've also printed up a number of demonstrator articles, test articles that represent real components in different systems. We also have completed TGA, thermogravimetric analysis, in order to determine the debinding temperature, the temperature at which our polymer vaporizes and leaves the matrix. Now, as we transition to phase 2 of this project, there's 2 key aspects that we want to work on. One is to actually start doing vacuum debinding and sintering. And we have a number of options that we're going to explore. From doing debinding here on campus, and then doing vacuum sintering over at AFRL using their facilities, to using an external partner or an external company to do commercial debinding and sintering and vacuum for us. And then finally, we're also looking at the procurement of a microwave vacuum furnace, which should be a very energy efficient way and also reduce the time to do debinding and sintering, specifically for space applications. The last major aspect is to print up much larger demonstrators, more demonstrators that are more relevant to application, demonstrators that are optimized based on our print parameters, so that we can produce parts that have the best dimensionality. Also, to print demonstrators that correct for the shrinkage that we see when we debind and sinter components.